Okay, this screencast is going to talk about the Haber process. All right, and hopefully, or maybe not, I don't know, you remember that the Haber process is the reaction between hydrogen gas and nitrogen gas, setting up an equilibrium with ammonia gas. All right. The products that this ammonia goes in to make, for the most part, is fertilizer, but it also goes to make nitric acid, which is a raw material for an awful lot of chemical processes. All right. And in any chemical process, what you desire is a high yield in a short amount of time. And in a chemical process, sometimes you have to balance those two out, because this high yield, when you're talking about an equilibrium, you really want to shift the equilibrium to the product side. And making product in a short amount of time really means you want to make that process go at the fastest rate possible. So in looking at this process, and I'm going to drop the state signs for now. Oh dear. It's 2 NH3. All right, so looking at the yield, to increase the yield, meaning to shift the equilibrium to the product side, you would increase the pressure. Remember Le Chatelier's principle? Increasing pressure in a gas system is going to make the equilibrium shift to the side with the smaller number of moles of gas. In shifting this as well, this does increase your yield. It also increases the rate of the reaction because you have your number of collisions increasing. Okay, so that's a win-win. So you're going to try to run this process at the highest possible pressure. All right, now what happens if we increase the temperature? One thing I forgot to give you guys is the change in enthalpy of the process. It is an exothermic process, negative 92 kilojoules per mole. So increasing the temperature, since it's exothermic, you can view that as having heat as a product. Increasing the temperature is going to decrease my yield because it's going to shift the equilibrium to the reactant side. However, increasing the temperature will increase the rate because you're increasing the number of particles with the correct or higher activation energy. All right, but you are going to decrease that yield. All right, so it's really because of this aspect that we have to kind of balance these two together. Oh, and the last thing that chemical processes will look at is the catalyst used. Okay, and any catalyst, if it works, is going to increase the rate, and there is no effect, if you remember, on the equilibrium because it's really going to lower that activation energy, increases the forward and the backward rate. All right, so you kind of need to determine what the optimum temperature is. All right. There is an issue with high pressures. These are expensive to operate, and they also involve expensive equipment. When you have to build a reactor that can be operated at high pressure, the engineering, the materials are a lot more money than one that's going to operate at atmospheric. All right, and getting back to the catalyst, the process uses iron, okay, and typically powdered, because that is going to increase the surface area. Okay. So, what the industry has developed is your temperature and pressures are going to vary country to country depending on how much they can afford. But typically the temperatures are going to be around 350 degrees Celsius to 450 degrees Celsius, and your pressure is going to be about 150 to 250 atmospheric. Now the overall point to this is to remember that you want to increase your yield and increase your rate. Sometimes those are going to be opposite. You know, if you increase the yield, you might impact your rate, and you have to find the optimum between that. And it's interesting that even with these, the yield only happens to be about 15%. So what they end up doing is taking the liquid, they cool the process down, remove the ammonia, and they recycle the gas. And by recycling, I'm not going to be able to fit that in, but that's recycling, you bring the yield up to 85%, which is an acceptable rate. The next process that we're going to talk about is the contact process. And this is used in the process to make sulfuric acid, which is a raw material that's used as a starting point in a lot of chemical processes. The process is starting with sulfur dioxide gas, reacting it with oxygen, and this sets up an equilibrium with the sulfur trioxide in the gaseous form. The enthalpy change is negative 192 kilojoules per mole, so it is a exothermic reaction. Okay. High yield is going to happen with a high pressure and a low temperature. And that's going to shift that equilibrium. Both of these will shift the equilibrium to the product side. Okay. Now, that's for the yield. How about for rate? We want to look at high pressure. Well, that's good because that works in our favor. But for the rate to be high, we would prefer a high temperature. Again, that has to do with the activation energy. And more collisions. Okay. So what they've found out is, going back, and a suitable catalyst, forgot that part. Okay. So for the contact process, they tend to run the temperature at about 450 degrees C. I don't even know if you see that sometimes I click the wrong thing. The catalyst is vanadium 5 oxide, and the pressure they run at is about 2 atmosphere. And that's very different than the Haber process, if you remember. It was 120 to 200 atmosphere. So they run it at about 2 atmosphere, and that gives a yield of about 98%. So quite a large yield, right? H2SO4, sulfuric acid, is used in fertilizer, detergents, and soap. Okay, and then the next screencast will be on, actually, we can continue here. No, we'll make it another one. It'll be on liquid vapor equilibrium, but it'll be a short one.